we're going to go over rational and irrational numbers today. Um, I included this comic just because it's kind of like somewhat relevant to what we're talking about. In that, with the irrational numbers, we're expanding our number system. And so, like with our beautiful little number line that we have here, you see that there's a lot of different, like, extra letters and comments on it. So we're expanding our number system so that we can understand some of these other things that are in here. So let's go through today's goals. Our goals are to be able to explain rational and irrational numbers, and we're also going to perform operations with rational and irrational numbers. This won't be too bad. It's just like adding and subtracting normal regular numbers. So let's talk about rational numbers. We have this beautiful little chart over here, and I'll explain it as we go. So a rational number is a number that can be written as a fraction. So you'll notice here, let's see, that we have our set of rational numbers. So we have this beautiful little circle that contains all real numbers. Here we have rational numbers. So most of the things that we've been dealing with, actually everything that we've been dealing with so far, is a rational number. So it's something that can be written as a fraction. It's a ratio of two integers. So an integer is a whole number, and it can be either positive or negative. A whole number is just like 1, 2, 3. There's no fractions. There's nothing else in there. An integer is a whole number, but it can be positive or negative. Most of our everyday numbers are rational. So 2 and 4 and 5, these are all things that are technically rational. And yeah, so here's some rational examples. We have some numbers. We can write these as a fraction. So our number 5 can be written as a fraction of 5 over 1, so it is rational. 1.333 can be written as a fraction. So that's 1 1/3, or in other words, 4/3. So that is also a rational function. We have 0.111. This is actually surprisingly a rational number, so it repeats. It's a nice fraction. It's actually 1/9. So since it can be written as a fraction, yes, it counts as being a rational number. We have negative 0.3. So this has a negative number, but that's not that big of a deal. We can write that as 3 over 10, and that works. So 3/10, negative 3/10, and that is a rational number. 0.001, well, that is actually 1 over 1,000, which again, since we can write it as a fraction, is a rational number. So these are all examples of rational numbers. Irrational numbers are these numbers over here. So they're a part of our real number system, but they're completely different. So you have our rationals over here, irrational are on the other side. An irrational number is a number that just can't be written as a simple fraction. So ir meaning like not rational, so it's not a ratio, and ratios are just fractions, so that's where it comes from. Here's a nice little hint that if we have an infinite and non-repeating decimal, it's irrational. So if you can't find any pattern in it, it's probably an irrational number. Here's some examples. On these ones, I got lazy. So pi is actually written as 3.1415926, etc. It doesn't actually like stop there, it keeps going. If it's rational, no, it's not. Because it doesn't stop, you can't actually write that down. Pi is just, it's easier to write it as the letter pi. E is another number. It's Euler's number. Now, it looks like there's a pattern here, but you go a little bit further digits in there. It's not, so it's about 2.718281828, and then it screws up. That one's still not rational. Here we have phi, which is the golden ratio, which is 1.6180339. That's still not going to repeat anytime soon, so that's not rational. We can't write that as a fraction. Square root of 2, you'd think, oh hey, we can do this. Well, it turns out the square root of 2 actually is just this nice decimal of 1.4, some other stuff. It doesn't repeat, you can't write it as a fraction, so it's not rational. This, if you were to think about it, so you have a Say you have a box with an area of 2, then you'd want square root of 2 on both sides so that the area is 2 and the sides are 1.414. And so that's like where it coming into handy and where you apply it. Square root of 3, same thing, 1.73. That's also not going to be rational. So here's some fun ones. We have Archimedes constant, aka pi. We also have the golden ratio, which is phi. So here you can kind of see it in a tulip, or not in a tulip, in a rose where it has that nice little spiral. That spiral actually comes from this Fibonacci sequence, or the golden ratio. Here you can see it as well, where it has like a nice little spiral going along with it. So this is like a really common one in nature. It looks pretty because it's such a perfect ratio. That's why it's called the golden ratio. Here we have Euler's number, E. So this is the thing for exponentials. When you hear something is growing exponentially, it has to deal with, it generally deals with Euler's number, this E. So like this e to the x has this really nice exponential shape to it. It just keeps growing. Let's do a quick check. What I want you to do is state if these numbers here are rational or irrational. Remember, if you can write them as a fraction, they are rational. If you can't, they're irrational. So go ahead and pause and take a moment to figure out which ones are rational and rational, irrational,